This lesson is a continuation of measures in a circle, and the objective is to calculate arc measures using inscribed angles. Just like central angle questions from the previous lesson, you actually could be looking for the measure of an angle or the measure of an arc. So what's an inscribed angle? An inscribed angle is an angle whose vertex lies on the circle. The intercepted arc is the piece of the circle formed by the inscribed angle. So let's look at yesterday first. If this circle has a center of B, then the central angle is angle ABC. And the minor arc is arc AC. So we know that if we knew the measure of the central angle, we would also know the measure of the minor arc. We're going to still talk about the same arc, but now instead of going from the center, we're going to go from on the circle. So we're going to go from point D to point A, point D to point C. So this is called an inscribed angle. We know that a central angle is made up of radii, an inscribed angle is made up of chords. This arc right here is now called an intercepted arc. I know it seems kind of weird because it was just a minor arc a moment ago. And it is still minor, it is still going to be part of the central angle. But when talking about an inscribed angle, we call it an intercepted arc. And it's not limited to the degree values at all. It just depends on where the chords lie. And so a minor arc, remember, is limited to less than 180 degrees. Now you'll notice that I am now twice as far away from the arc than I was. I was here and I'm twice as far away. And so that means that the angle is getting smaller. It's like a rubber band, it's being pinched as it's being stretched. So the measure of our angle, ADC, is now not the same as our intercepted arc, because as we pull up, you can see that the angle is getting smaller. The arc hasn't changed. So the angle is now taking that same arc and cutting it in half to get its degree value. Remember, this has everything to do with degrees of rotation, and so you don't have to rotate as far to get through these same degrees. You're only going to rotate half of that amount to get that angle. So what happens if, because remember I just said the inscribed angle is not limited like a minor arc, I just mentioned that the intercepted arc is not limited like a minor arc, it just depended on where the chords were. So what if the chords are in such a manner that they terminate at the ends of a diameter? So you can see I'm kind of making a little triangle here. Remember that a diameter causes a semicircle, and a semicircle is 180 degrees. We just said that the inscribed angle would be half of the arc that it intercepts. So half of 180 is 90. So there's a theorem that summarizes that. It says inscribed angles that intercept a semicircle are right. So I kind of informally proved that, but that's the theorem. Inscribed angles that intercept a semicircle are right. So let's look at some examples. So our vertex is on the circle. I'm using two chords. This is an inscribed angle, and inscribed angles equal half the arc that they cut, so half of x. I'm going to go ahead and multiply by 2. So x is 120 degrees. So as I'm rotating 60 degrees here, I'm actually rotating 120 degrees here. Number 2, I'm using a diameter and a chord, so basically 2 chords. So here's my inscribed angle. So the measure of angle DAC has to be half of the arc it's cutting. So here's angle DAC, and here's the arc that it's cutting, so it's half the measure of arc DC. Measure of angle DAC is x, and so it's half of arc DC. The problem is I don't currently know it, but I do know that this is a diameter, so arc AC all the way from A through D to C is a semicircle. So we know that this is 180 degrees, but I've already used up 110. So this little arc here is the 180 minus the 110, which is 70 degrees. So the measure of arc DC, the measure of the intercepted arc, is 70 degrees. Can I take half of 70? Sure can. So x is 35 degrees. Number 3, you can do the algebra or remember the theorem. If I identify this as a diameter, this arc is a semicircle, and if it's a semicircle, then this inscribed angle is right, and right angles are 90 degrees. So you can just say that. You can go straight there. That's why we have that theorem, to reduce our workload. So let's review one more time. If your angle is on the circle, if it's made of 2 chords, it's an inscribed angle. The arc that it cuts is called an intercepted arc. The intercepted arc will rotate faster because it's farther out. It's twice as far out from the pivot point. And so if we can cut it in half, we will know the measure of the angle. The angle is going to be the smaller one because it's not rotating as fast. So before I was rotating here at the center, and now I'm rotating here. So I'm getting a longer rotation in degrees, so I've got to cut it in half to figure out how far I've rotated in my angle. Some other things that you can do with these concepts of an inscribed angle is half of its intercepted arc is take a multi-picture and figure out where there's a pair of congruent angles. So basically what we're going to do is we are going to look for, sorry for the hesitation here, we're going to look for 2 inscribed angles that have the same intercepted arc. Or I actually do it the other way. I find an arc. So let's just say this arc right here. So I'm going to look for an arc, and now I'm going to look for 2 angles that cut that arc, 2 inscribed angles. So I know I'm starting at R. I can't go to here because there's no name, plus it might be central. I want it to be inscribed. So I start at R, go to U, and then to S. So angle RUS. Now where's the other angle? R, instead of going up to U, I went R to T to S. So they are congruent because they are both intercepting the same exact arc. Do you see the other pair? Let me remove some of my marks. Do you see the other pair? Okay. So let's look at this arc. And I know some of you are asking, well, why didn't you use arc ST? I mean, it could work. It could, except there aren't any angles going down to arc ST, except for this one, and we don't know where that one is. We don't know if it's central, or so we can't go that way. So arc UT, so URT, angle URT is congruent to, instead of going U to R, we're going to go UST. And so using inscribed angles and intercepted arcs, you can actually find a set of congruent angles.